So, hello everyone. So today we will talk about Künneth formula. So this is an important result, um, and so this is I will use this result mainly in my main presentation on group homology and cohomology. So this is just like a prerequisite for that. Okay, so let's just start. So, so first of all, recall this notion of tensor product of two chain complexes. If I have two chain complexes P and Q of right and left are modules, I can take their tensor product, and this tensor product chain complex is P tensor Q. The nth component is nothing but this direct sum P plus Q equal to n of PP tensor QQ. And the differentials, to define the differentials, well, you define as follows. You take an element, have to define a map from this to this. So here you take an element from PP tensor QQ, let's say X tensor Y, you define it on just one component in the direct sum, and then you define the differential dn as d of x tensor y plus minus 1 to the power p x tensor d of y, where d is the corresponding differential on p, so it's like, and d here is the corresponding differential on q sub q, right? So that is, you can check it's a chain complex and so on. Alternatively, it can be viewed as this total complex. First of all, take this double complex, double complex consisting of PP tensor QQ at the PQth position, and then just take the total complex. Take the diagonal element, direct sum of them, which is precisely this thing, off diagonal. So this is the total complex of the double complex. That's another way to see this. So this is the tensor product of these chain complexes. Now, um, Künneth formula, what it does, it gives a relationship between the homology of this tensor product P tensor Q, this one, to that of the homology of P and on the homology of Q. So what does this say? Suppose you have this situation P and Q are chain complexes, and Pn and the image of every Pn, dPn, are flat R modules. For every n, they are flat R modules. Then you have an exact sequence. So this sequence, as you can see, this is just tensor product of individual homologies. Take the direct sum, and then here taking the nth homology of the total tensor product. And here this is some correction term regarding some torque correction term. Okay, and moreover, it says that if your ring is a PID and this is a complex, P is a complex of free R modules, then this sequence actually splits. Although it splits non-canonically, here non-canonically means that to get the explicit map of splitting, you have to make some choices. So that is there. So let's try to see a proof. Now here, I will only prove, because of lack of time, I only prove the first part. The second part, you can look. So for a special case of the second part, where the complex Q is just one module concentrated at degree 0, for that case, in that special case, you can look at the proof in the Weibel's book on homological algebra, Charles Weibel's book. But if you want to see the general result as stated here, for then you can look at the proof in the book titled Homology by Saunders Macklin. Okay. Anyway, so let's just prove the first part here. So see, first of all, that this P is a flat R module, therefore this tensor product is a flat exact functor. And hence, if I take the homology, the nth homology of this chain complex. Now what is this chain complex? Here I'm considering this PP as just one chain complex with degree P element being PP, but everything else being 0. So then I'm taking the tensor product of these two separate chain complexes. Essentially, it's a chain complex whose nth component is PP tensor Qn minus P. And so maps are there. So it's like PP is there, but this is Qn minus P, the nth component of this thing, not Qn. So of course, since PP is tensor, this is an exact functor, and homology commutes with exact functors. I can bring the homology there to get this is isomorphic to PP tensor Hn minus P. Note, I get n minus P of Q. Now, assume that for the time being, we are in a special case where all the differentials on P is 0, which means that the homology of P at P is just P of P. Also, in this case, the differential maps in the tensor product chain complex, they simplify, right? The dn of x tensor y is, the d of x is 0, so it just becomes minus 1 to the p x tensor dy. And then you can see that essentially you can view this tensor product as just tensor product chain complex as just a direct sum of a bunch of chain complexes, which is pp tensor q. So essentially you have these maps, because all you're doing is that x is fixed here and only y is changed to d of y. This minus 1 doesn't play much role. So this is like at the pth component, this chain complex is the direct sum of pp tensor q and the map goes from pp tensor q to pp tensor q to pp tensor q minus 1. So only these maps are important. So okay, so that's fine. So then the homology of this tensor product chain complex, since it's a direct sum of a bunch of chain complexes, this is direct sum of, since the homology commutes to the direct sum, I can bring the direct sum outside to get this nth homology of pp tensor r q, which we know already is just direct sum of pp tensor hn minus p of q. But now since p is but now you can write pp as just the homology, right, because it's zero differential. So you get this thing, and that's exactly what we wanted, right? In this case, the tau terms, there's no tau term. I mean, if you apply this case when the differential is zero, the homology is just p. This is pp and this is q. I don't care what this, but this is pp. The point is, since it is flat, the tau will vanish. So this is just a zero automatically. So all I'm concerned is this isomorphism, which I have managed to prove in this special case. This isomorphism. This is isomorphic to this. Now, let's consider the general case now. Suppose Zp and Bp we denote by the cycles and boundaries of this chain complex. Well, that's standard notation. Now, obviously, we have this short exact sequence 0, Zp, Pp, Bp minus 1. Now, since these, by the assumption that is already given, hypothesis Pp and Bp minus 1 is are flat modules, uh, you can apply the long exact sequence of Tor here to observe that this Zp is also flat. Alright. Then fine. Now let's tensor this short exact sequence by some module. Let's say Qn minus P. It could be any arbitrary module. Then I know the tensor product is right exact, so I will start from here. So it will still be surjective, this map, but I'll tensor it with Qn minus P. And here, oh, here I should get a Tor term, right? I should get a Tor sequence should start from here. But the Tor term should be Tor 1R of what? Of Bp minus 1, comma Qn minus P. But Bp minus 1, remember, is a flat module, so the Tor vanishes. So just like that, I tensor this Qn minus P and I get a flat, and I get an exact sequence. This is also exact. So, okay. Then I can take direct sums, right? I can say direct sum of exact sequences will remain exact in the category of R modules. So I do a direct sum with P and I get this thing. Now notice this is the nth term of this chain complex Z tensor Q. Z is the chain complex consisting of all these ZPs rather. Of course, the differentials are 0. Similarly, B minus 1 is the chain complex of B's. Of course, here the pth degree element is BB minus 1, shifted by minus 1. And the differentials are also 0. So this chain complex, because I've shown that every nth term gives an exact sequence, this entire chain complex sequence is actually exact. Okay. Now, once you have this short exact sequence of chain complexes, I can get a homology long exact sequence. So part of which is written here. So I write this homology long exact sequence in this way. These are differentials, delta. Now, since these, as we see, observe that these complexes B minus 1 and Z, they have 0 differentials, by early observation, we know what Hn Z tensor Q should look like. Right? By early observation, we know that if a complex has 0 differentials, then Hn of P tensor, if P has 0 differential, then Hn of P tensor Q is this direct sum. So now we rewrite this. I just noted this thing. I rewrite this as direct sum P ZP tensor Hn minus P Q. This remains the same here. This again I rewrite as direct sum P BP tensor R Hn minus P minus 1 over Q of Q. And again this I rewrite as direct sum P ZP tensor Hn minus P minus 1 using that above observation. Now what happens to these differential maps? Now since you explicitly can find what these differential maps are. Remember how we proved this result that a short exact sequence of chain complex is a long exact sequence? You use the snake lemma, and in the snake lemma to construct this homomorphism delta, you for the category of R modules you can have explicit maps, these maps in the snake lemma, and hence maps in this homology long exact sequence. When you use that explicit maps delta, you show that this map right here is nothing but the map induced by the inclusion of BP into ZP. So the BP includes in ZP, and so this map is just given by, for each P you have this map from BP tensor this to ZP tensor this and take the direct sum. So that is this map. Similarly this map. Okay, fair enough. Then from this short exact sequence I can get a long exact sequence, I can get a short exact sequence. Essentially what I do, I look at the co-kernel of this map, this to this. I have a co-kernel here. I take the co-kernel of this map, I call this In tensor Q. So this is the co-kernel of In tensor Q, and this inside H and P tensor Q. And then I look at the kernel of this map. This is kernel of this map. So that will be something here, and that I call kernel, of course, kernel of In minus 1 tensor Q, and I take. So this is short exact, obviously. So now our main aim is to figure out what these co-kernels and kernels are, right? So that will give me an exact sequence with the middle term, what we want. So for that, okay, let's go back and look at this particular short exact sequence: 0, BP, ZP, HP. This is the definition of the homology, right? This is a short exact sequence. This is the co-kernel essentially of this inclusion. Now, if you apply the long exact sequence for tau on this short exact sequence, what happens? First of all, you tensor this by what? I tensor this, again, I can tensor this arbitrarily, but let's tensor this as h n minus p minus 1 of q. If I tensor this thing, the n minus p minus 1 q, this remains exact, right? Because this tensor product is that exact. This I get fine, this is fine. Here, I'll get a tau term. So that I write it down. And here also I get a tau term, but the tau term will be tau 1r of zp comma hn minus p minus 1 of q. But zp, remember, we showed earlier, is flat, so the tau term will vanish. So I'll get 0 here. So therefore this is the long exact sequence that I'll get. The point is it is exact, and since again taking direct sums on exact sequences still give an exact sequence, when I take a direct sum with p, I'll still get an exact sequence. Now, of course, when I take a direct sum, this map from BP tensor hn minus p minus 1 q to zp tensor hn minus 1 hn minus p minus 1 of q is this map In minus 1 tensor q, and that's the map which is coming from the direct sum of each individual inclusions induced by BP to ZP inclusion, essentially. Not necessarily inclusions, the point is you have this map BP to ZP and then you tensor this, right? And then take the direct sum. So that is what I get here in this long exact sequence. This is the map. So this is the map whose co-kernel and kernel I want. Now, if I find the kernel, so what's the kernel of this map? So the kernel is, by this, since this is exact, the kernel is nothing but this tau term. So this kernel of In minus 1 tensor Q is this tau term. So this goes here. Similarly, I want to find the co-kernel. So the co-kernel of this map is, of course, since this is exact, this term, this direct sum HP tensor Hn minus P minus 1 Q. So this, but notice that here I want the co-kernel of In tensor Q, not In minus 1. So all I want is that here n should be replaced by n minus 1 should be replaced by n. So that is the thing. So I just put here this thing exactly in the co-kernel place, but n is just n. So n minus 1 should be right n. So this is direct sum of P, HP of P tensor Hn minus P of Q. So that's it. But we wanted to 0 tensor this direct sum, which is equal to this thing, and the middle term was already there, and the torque correction term is this thing. So that proves this first part of the theorem. Alright, now let's see some applications, the so-called universal coefficient theorems. Directly I apply Künneth formula to prove this. Suppose theorem says, suppose R is a PID and P is a chain complex of free R modules. Alright, then I apply the Künneth formula, where I take P to be P and Q I take to be the chain complex with just one module M, concentrated at degree 0, because I'm just working with one R module and one chain complex. And then notice that since I'm working with a PID and these are free modules, I can apply the second part of the Künneth formula to get actually not only an exact single or split exact sequence. So this gives me this non-canonical isomorphism of this homology of P tensor M with homology of P, the relationship between these two homologies. Right? So this is HNP tensor M direct sum with this torque correction term. So that's the universal coefficient theorem for homology. Now, if you look to the proof of Künneth formula in the special case when again Q is an R module concentrated at degree 0. We worked for a general chain complex Q, but Q could be just one simple chain complex where everything is 0 and just at the 0th degree you have this module, any module M. Then, and you can work with, and instead of working with this tensor product, we can work with the Hom functor in that case. And then in a very similar fashion you can prove, just like we proved the Künneth formula, you can prove this universal coefficient theorem for cohomology. So what I say is that if you have a chain complex of projective R modules such that the images are also projective, that actually projective fact gives you the splitting, then for any R module you have this split exact sequence. Again, it's non-canonical. Again, it's similar. The middle term, however, is the cohomology of this Hom now. So this is again a chain complex P of P comma M. This will be a co-chain complex because we are applying the contravariant functor to a chain complex. So I'll talk about the cohomology. But mind you, here and here I'm still taking homology because it's a chain complex, right? And in the proof you'll only get homologies. There's no reason to get cohomology. So this, of course, the situation is reversed. Here I get hom, here I get x. There was tor. There was this tensor product here. There was, so this is reversed, but it should be what you expect because it's a dual. Yeah, for tensor, instead of tensor we're going with hom factor. So this is the universal coefficient theorem for cohomology. And all this comes from this Künneth formula that we talked about earlier. Okay, so that's it for this. Thank you.